All right, it says HCN has a Ka of 4.9 times 10 to the minus 10. What is the pH of a solution which contains 0.35 molar NaCN? So here we're starting with some Cn minus. It's reacting with H2O to form the HCN and the OH minus, and we're actually given the Ka of the HCN. But what we actually need is the Kb value. And the reason that we need the Kb value is because we're given the conjugate base. So the first thing we want to do is find the Kb. Well, it turns out that the Ka times the Kb equals the Kw, which is 1 times 10 to the minus 14. So what we can do is we can find the Kb value from the Ka, specifically the Ka equals the Kw divided by the the Kb equals Kw divided by the Ka. It would be the other way around too, but we want to solve for the Kb. And then this is 1 times 10 to the minus 14. The Ka is provided, 4.9 times 10 to the minus 10. And when we do that, we get 2 times 10 to the minus 5. So this is the Kb, because in this case we're adding the conjugate base of the HCN, okay, in the form of NaCN. Na is just a spectator ion here. Well, now we have the Kb. We also know the initial concentration of this. Now this is the exact same question as we had 2 questions ago at this point. So the initial concentration of Cn minus is 0.350 molar. The initial concentration of HCN is 0. The initial concentration of OH minus is 0. We're going to gain some X of this. I keep doing that. We're going to lose some X of this. We always lose reactants. And we're going to gain some X of each of the products. We're going to end up with X here. We're going to end up with X here. And if this X is less than 5 to 10% of this, we can ignore it. And here in all these examples, we can ignore that X. So we just get the 0.35 molar here. So we don't have to use the quadratic equation. Well, now we need to write the Kb expression, which we haven't done yet. So the Kb is going to be equal to the concentration of HCN over, times the concentration of OH minus over the concentration of Cn minus. We now know the Kb, we know these are both X, and we know the Cn minus, so we can plug in. So the Kb is equal to X times X, these two X's, divided by 0.350, the concentration of the Cn minus. All right, I should have plugged in the Kb. So the Kb is equal to, right here, 2 times 10 to the minus 5. We cross multiply, and we find that x squared is equal to 0.35 times 2 times 10 to the minus 5, which is 7.1 times 10 to the minus 6. We take the square root, and we find that x is equal to 2.7 times 10 to the minus 3 molar. Well, what is this? This is the concentration of OH minus. So this is the concentration of OH minus. We're looking for the pH. Well, we can find the pOH is the negative log of the concentration of OH minus, which is the negative log of 2.7 times 10 to the minus 3. And we find that the pOH is equal to, in this case, 2.57. But we're not asked for the pOH, we're asked for the pH, and the pH equals 14 minus the pOH, which is 14 minus the 2.57, and the pH is equal to 11.43. So in this case, we found the pH of this solution, which is exactly the same as 2 questions ago. The only difference is that we were given the Ka of the weak acid, but we had a conjugate-based solution. So we needed to convert that Ka into a Kb. Once we converted it into a Kb, we could just use it exactly the same as in the previous base example. All right, and the reason we had to do that is because we have an NaCN solution, which is Cn minus the conjugate base, not an HCN solution.